reach the critical temperature Tc of the superconducting material. Now the differences in the energy between the free state of the electron and the paired states appears the energy gap at the Fermi surface. Now at the Fermi surface, the normal electron states are above the energy gap, while superconducting states is the below the energy gap. Like this is a 3 steps. Middle steps is the energy gap, below superconducting state, and above is the electron states. Now at absolute 0 Kelvin, the pairing is complete, and hence the difference in energy of free and paired electron states, that is normal and superconducting electron states, is maximum. The BCS explain the existence of Meissner effect. Generally, Meissner effects is the irreversible effect. If the specimen is lose its magnetic field, then temperature is increases above the critical temperature. The material is also irreversible, that's why it's also becoming the superconducting material. Now coherence length and the energy gap parameters is also explained by the BCS theory, and it is the most important theory of this topic. Now here is the formula of the temperature. At temperature T is equal to Tc, the pairing is dissolved and hence the energy gap reduces to 0. Thus, across the energy gap there are many excited states for the superconducting in Cooper pairs. BCS theory solves the problem of the electron energy when the attractive interaction V is present and the expression for critical temperature is given by Tc is equal to 1. This is the equation of the Tc, 1.14 theta d exponentially minus 1 divided by V into N, and in this equation theta d is the d by temperature and N is the density of the electron and the Fermi surface is the V. Net result is the attractive interaction. Accounts for the isotope effect theta d is directly proportional to the m raised root of mass or weight of the superconducting material. Now second part is the high temperature superconductivity. This is the low temperature superconductivity, and the second part is the high temperature superconductivity. Few superconductors have been discovered between 1911 and 1986. The observed highest Tc had gone from 4 kilo temperature to about 23 Kelvin in the above period accomplished with the liquid helium. Actually, high temperature superconducting material is its critical temperatures is very high. Later, the material with Tc up to 40 Kelvin, 93 Kelvin and 125 Kelvin have been discovered respectively in the years 1983, 1987 and 1988. The new material with Tc crossing 77 Kelvin is more important since the cooling is accomplished by liquid nitrogen instead of the liquid helium. The above trend confirms that it might be possible to develop the superconductors at a room temperature. Now, high Tc superconductors. The superconductor having high Tc values like 42 Kelvin above 90 Kelvin near about 125 Kelvin. The high Tc superconductors are not metal or intermetallic compounds, but they are oxides of the copper in combination with their elements. As a result of the combination, the ATSC materials become brittle and it is easy to form wires and taps. The ATSC wires provides a transmission of electrical power over a long distance without any resistive loss. This is the some high temperature superconducting materials and its structure. In this table, first material is the lanthanum strontium copper oxide. Its structure like a tetragonal and its parameters there is given, and its critical temperature is 38 Kelvin and its crystal size is 13.25 angstrom. Now the second material is the Y123, it means yttrium barium copper oxide, and its structure like a orthorhombic structure. Its parameters is 3.81 and A side parameter is 3.81 and B side parameters is the 3.88, and its crystal size is 11.63, and this material have a 19 Kelvin critical temperature. Now the third one is the titanium barium copper oxide. Its structure is the tetragonal structure and its A side parameter is the 3.83 and its crystal size is 19.68 and its critical temperature is near about 80 Kelvin. Now the next material is the titanium barium copper oxide. It's also called the titanium 1234 and it's also structures like a tetragonal, and its size is the crystal size is the 15.88 and its critical temperature is near about 105 Kelvin. Now the second one is the material is the titanium 2212 and it's also called the titanium barium calcium copper oxide. The structure is also tetragonal and A side is the 3.86 and its crystal size is the 23.24 and its temperature is the near about 15 Kelvin, and it is the now next is the titanium 2234. It is called titanium barium calcium copper oxide. Its also structure have a tetragonal structure, and the A side is the side preference is value is the 3.85 and its crystal size is the 29.39 and its critical temperature is the 108 Kelvin. Now the next is the also titanium 2223. It means titanium barium calcium copper oxide, and its structure is also tetragonal and its A side preference is also 3.85 and its crystal size is the 35.60 and its critical temperature, it means transition temperature, is near about 125 Kelvin. Here is the one observation is the titanium have all type of titanium type chemical formulas. Structures have a tetragonal structure. Now next one is the Bi2201, means bismuth strontium copper oxide. Its structure is the orthorhombic. Its A side preference is the 5.36. Now the next one is B side preference is the also 5.37 and its crystal size is near about 24.62 angstrom, and the critical temperature Tc for this chemical formula is the 6 Kelvin and it is the low temperature superconducting material. Now the next one is the material is Bi2212, means bismuth strontium calcium copper oxide. Now these chemical formula have structure also orthorhombic structure. Its A side preference is the 5.50 and B side preference is the 5.51 and its size is the 30.78 angstrom. And this critical temperature is 81 Kelvin. And the last one is the bismuth strontium calcium copper oxide. It have also structure orthorhombic and its A side preference is the 5.40 value and have B side preference as the 5.41 angstrom, and the C is the 37.18 and its materials have critical temperature is 110 Kelvin. These all are the high temperature superconducting materials. Now the applications. Due to vast development of superconducting materials, they find a large range and diversity of application in different fields. Following are some of the important applications. Here the structure of the high temperature superconducting material like Y123, like these yttrium, barium, copper oxide. This is the structure of high temperature superconducting material. In this structure, here the black ion is the La2. Here the La means the rare earth ion, M is the any superconducting material, copper oxide. This is a tetragonal crystal structure. Now the superconducting magnets. Current flows through a coil, generates magnetic fields. This is the property of the superconducting material. Like current flow, when the current is flow in material, superconducting material, when the magnetic field is removed, then many times the current is continuously flow in superconducting material. This is the one type of electric property of this material. Now the second thing is the coil is replaced by a superconducting material, it generates a large magnetic field. Now the second point is conventional high field electromagnets. Joule heating is a major problem, but while in superconducting material the current flow without any resistance loses and Joule heating. That's why the superconducting material is many times current flows is the best material as a normal magnetic material. Widely used superconducting materials type 2 niobium and titanium and the Nb3Sn. The important application of this type of superconducting magnets in the NMR. Now the medical diagnostics and spectroscopy, magnetic levitations and the magnetic shielding, etc. Now the applications of superconducting material, one of the most important applications is the Josephson's effect. Now Josephson effect, it's a one type of sandwich in between two superconducting material and a DC voltage is applied on this superconducting material. This effect is found out in 1908 by Brian Josephson. Now the current flowing through the device has both AC and DC component. It is called AC Josephson effect and also DC Josephson effect. Now the Josephson effect, the AC component exists only during the existence of the applied voltage V, while the DC component persists even after the removal of applied voltage. This is the difference between AC Josephson effect and the DC Josephson effect. The frequency of the AC components is G is equal to 2 electron volt per hour irrespective of the material used, and hence the value of the E by H can be determined more precisely. Now the superconducting quantum interface devices. It's also short form in Squid. Squid is a magnetometer, involves supercurrent properties of the Josephson junction. This is a figure of the Josephson effect. Here is the oxide superconducting material and what voltage is applied on this material. Here is the middle oxide insulators is becoming a typical Squid system used for a sensing magnetic field. The two temperature superconductors are being used for fabricating this Squid. The main application of Squid are to detect a small fractional change in flux geologically layers in different minerals, to detect NMR signals at a low temperature. Here is the NMR is the instrument of the find out the value, and its work on this type of magnetic material. Now the second application is the maglev. Maglev, it behaves like a levitations. Maglev is the acronym of magnetic levitations. Now what is the levitations? When a magnetic field applied on a specimen, and when the magnetic field magnetic lines is ejected from the superconducting material, like the becomings like a levitations, like maglev trains. It is also called the effect of levitations. So the maglev is the acronym of magnetic levitations. Now here is the system of the levitations is Squid sensor, field sensing coil, and the systematic represents of the maglev systems. In this system, the Squid sensor, field sensing, and the liquid helium in this tube. Now the separate up to the 100 meter. The tube length is the output indicators. Here is the output indicators and the control units. Now maglev, a system used to run the vehicle leviated from the guideway, the rail tracks of the conventional railways. It's the best examples of the maglev train. Now the principle behind maglev, the electromagnetic forces between the superconductivity magnets, and the maglev systems consist of 8-figured cavitation coils and sidewalk on the guideways. Now the guideways for the maglev similar to rail track. Here is the here shows in the figure, it is 2 rail track and the train. This is the figure of the maglev train. The guide and the on-board superconductivity magnets possess at a high speed with several centimeters below the center of 8-figured coils. Now the second point is an electric current is induced within the levitation coils. Now next thing is an electric current is induced within the levitation coils, but when the levitation coil acts as an electromagnet, produces an electromagnetic force which pushes the onboard superconducting magnet